All right, now we're going to be looking at compositions of trigonometric functions. So one thing to remember with compositions is essentially we are going from one domain, so like let's say this is our f of x, and then we arrive at another function, right, another domain. So our function, and actually let me write it this way. Our function, we are really going from this domain A to B, and really we're trying to land at C, right? So our function f of x takes us from A to B. Our function g of x takes us from B to C. So how do we go from our domain A to our domain C? We arrive by the composition of this function. So if you remember this from algebra, that's what's happening here. We are having a composition of functions associated to here. So if you remember, given a function f and its inverse, f inverse, if x is in the domain of both functions, then we know that f composed with its inverse is going to equal x. So essentially, if I'm taking the domain, so if I'm going from my domain to my range, right? How do I go from my domain to my range? Well, I use f of x, right? And then how do I go from my range to my domain? I'm looking at the f inverse. So basically, how do I do a U-turn? Right, so one way to think about that is we are kind of composing them. So we're going to take f of x, our inverse of x. Right, remember that inverse only exists if those functions are one-to-one, and that's why it's important that f is in the domain of both of those functions. So this is also true then if I take my inverse and I compose it with the original function f of x, then I will get x, right? And this helps define the definition of if two functions composed with each other are in fact inverses of each other. So when we're looking at trig functions, we have to keep in mind some properties. So let's take a look at this summarized here. So if in fact we have our domain, our x is going to be between -1 and 1. So if x is within this domain, then it's true that sine composed with sine inverse of x is equal to x. And this is true also if for cosine, right? So if x is between -1 and 1, then I can take cosine of cosine inverse of x, and that's going to give me the same, the input becomes the output, right? So for tangent, oops, actually, I shouldn't be doing the equals to, because remember, we can't equal infinity. So if x is between -infinity and infinity, then it's true that we can take tangent inverse of x and then apply tangent to it and get the input becomes the output. Okay. Now I do want you to kind of take note of the order. Order matters here. So this is saying we are first applying the inverse function, and then we're applying the parent function, if you will. The inverse function goes first, and then our tangent, and then our cosine function. So here we have inverse, tangent, and then tangent. So now, looking at it the other way around, the domains change a little bit because I'm starting with the sine. So it always depends on which function you're starting with, right? So we always want to start with the innermost function. So here we're doing sine of x. So we know that x has to live between -π/2 is less than x, which is less than π/2. And then we're going to have 0 is less than or equal to x, which is less than or equal to pi. And then we have -π/2 is less than x, which is less than π/2. Okay, so again, it's because we're first applying that original function, and then we're applying the inverse. So that's the way that these equal each other. So we do need to pay attention to the order to make sure that it is within the domain of the first function. All right, let's take a look at some examples here. So for number 1, directions say find the exact value of each expression if it exists. So we're going to start off here with, this is saying I'm starting off with sine inverse of -1/3. So -1/3 is in fact between -1 and 1. So this tells me that the value, this will equal -1/3. So my input equals my output. Okay. Now I'm going to look at number 2. Notice I'm starting with arc cosine, so 2/5. So because arc cosine is what's inside, I need to make sure it's 2/5 between -1 and 1. It is. So therefore, this output will be 2/5. All right. All right. Looking at number 3, right? I'm starting with arc cosine. I'm looking at 3/2. Arc cosine has to be between -1 and 1. 3/2 is equivalent to 1.5. So it is not within that domain of that -1 and 1. So therefore, this does not exist. Okay, it's not possible, undefined. Okay. All right, try 4, 5, and 6. All right, so for 4, 5, and 6, I'm hoping that you've seen that the tangent we're going to be getting, because 9/2 is within negative and positive infinity, right? We do see that that output is going to be -9/2. So the input equals the output. Again, tangent, when I'm looking at tangent, 1/4 is definitely within that domain here, since I'm doing the inverse tangent first. So that's going to equal that. For arc sine, -7/6, right? So I come over here for my sine inverse, and that's not within this domain. So therefore, it does not exist. It's undefined. Okay. All right, let's take a look at number 7. So number 7, I'm starting with the sine function. So I'm looking at pi/4. I need to make sure it's pi/4 within my domain of -pi to -pi/2 to pi/2. And the answer is it is. So therefore, this is going to equal pi/4. Okay. All right, go ahead and try. Let's have you try 8, 9, and 10. All right, so as we look at number 8, 9, and 10, I hope we see that for 5/6 cosine, that is definitely within that acceptable domain. So our input matches our output. For our tangent function, we did have -pi/2. So thinking about the tangent function, remember, we have those asymptotes that are running at the pi/2. So therefore, this does not exist. It's undefined. Now let's look at sine of -pi/3, definitely within that domain of that sine function. So our input equals our output. All right, let's take a look at number 11 through 14. For this one, we are going to be looking and taking a look at our unit circle for some assistance. So if we kind of take a look at the note here, if the angle is outside of the domain, we write using an angle within the equivalent trig value that is in the domain. So here, we don't want to discount the fact that, so I have sine of 3pi/4. Sine of 3pi/4 is not within the domain of sine. So let's take a look at the unit circle. All right, so for the sine value that we're looking for, so that 3pi/4, so this is the sine value. So remember that the sine of 3pi/4 is going to equal the y value, which is going to be √2/2. So this value is not within the domain. So I want to come over here. Remember, the domain of sine, we're looking at quadrant 1 and quadrant 4. So where does sine also give us an output of √2/2? Well, that output of √2/2, positive √2/2, is going to be that pi/4. Right, so we can kind of rewrite that 3pi/4 as pi/4. So for this particular value, our original was arc sine of 3pi/4. Oops, sorry, I dropped the sign. Arc sine of 3pi/4. And so this arc sine of 3pi/4 is going to turn into, we can rewrite this as the arc sine of pi/4. And so now this is really, and if we kind of want to see the steps happening, this is really saying I would evaluate this first. So when I evaluate that sine of pi/4, that's going to give me that √2/2. Right, and so now I'm looking, okay, what is arc sine of √2/2? And so this is really turning into, this is going to give us pi/4. So this value, arc sine of 3pi/4, is not going to give us the same output of that pi/4. I mean 3pi/4. It's going to give us the same angle within this domain from -pi to 2pi. All right, so we are going to kind of come back over here to our notes, and we're going to see that we're going to rewrite arc sine. We're going to rewrite it as arc sine of pi/4. And then we can use that property that because we're within there, that this is going to be pi/4. All right, let's take a look at tangent. So tan inverse of tan of pi. So tan of pi is not within that domain, right? We're going from negative pi over 2 to positive pi over 2. So we want to come back over here to our unit circle. So at our unit circle, when we think of tan inverse of tan of pi. So when I think of tan of pi is going to be looking over here. Remember, so tan of pi is going to be looking at our y value over our x value. So our y value here is 0 over our x value is negative 1. So we get tan of pi is 0. So where else do I get a 0 value for tan of pi? Well, I hope you see that tan of 0 would give us the same value, because I would get that 0 over 1, which gives me 0. So that means I can rewrite this as tan inverse of tan of 0. And now I can see that the value will be 0. So coming back over here to our notes, we're just going to go ahead and write that out. So we're going to rewrite this as tan of 0, which gives us that 0. Go ahead and try 13 and 14 on your own. All right, hopefully you did 13 and 14 and didn't think it was too cruel. But here we're looking at 11 pi over 6. So coming over here to our unit circle at 11 pi over 6, we are right here. So what would that equivalence be? So remember that when we're looking at our domain, we are looking from negative pi over 2 all the way to pi over 2. So really all we need to do is take this angle, the 11 pi over 6, and we are going to rewrite it as a negative angle, right? So instead of going to the circle this way, we're going to travel this way and get the same value. And so then we would just be rewriting this as a negative value. So coming over here, we can see that we've just rewritten it as negative pi over 6, which then tells us that our output's going to be that negative pi over 6. So here, when I'm looking at that negative 4 pi over 3, we do want to go back to our unit circle and say, what is that equivalent to? So for that negative 4 pi over 3, we're coming this way. Oops. So we're coming this way. All right, so that negative 4 pi over 3 is going to be equivalent to that 2 pi over 3. Okay. One way to think about the negatives is when you're figuring out what the negatives are, think about it if here is positive 4 pi over 3. So negative 4 pi over 3 is going to be reflected about this axis here. So I need to say, okay, well, where would that be reflected? Well, this is my third line here, so my negative value is going to be here. So this is going to be equivalent to negative 4 pi over 3. So we're just going to rewrite that angle there. So coming back over here to our notes, we see we're just rewriting that angle as positive 2 pi over 3, which tells us that the output is going to be 2 pi over 3. Okay. All right, let's continue here. So we want to find the exact values of each trig expression if it exists. So looking here, we want to start off with sine of pi over 6, and then we want to be able to take the cosine inverse of that value. So what is sine pi over 6? So sine pi over 6, that's going to give us 1/2. So now we're looking at cosine inverse of 1/2. What is that? So coming back over here to, let's look at our unit circle. Right. So I want to know, well, when does cosine function equal 1/2? And so I hope you see that cosine is going to be our x value. It's going to equal positive 1/2 here. So my value is going to be pi over 3. Okay. All right. Let's try one more, and I'm going to jump to number 17 here. So for number 17, we're looking at sine inverse of tangent of negative pi over 4. So coming to our unit circle, negative pi over 4. That's going to be similar to this one. So with my tangent value, I'm going to end up with our x over y. So our tangent of negative pi over 4 is going to be negative 1. So since it's negative 1, coming back to our value here, this is really going to be sine inverse of negative 1. So when does sine inverse equal negative 1? So sine is going to be our y value. And when does sine equal negative 1, right? So I hope you see that it's over here. And so what is that value? So that value is 3 pi over 2, but it's also known as negative pi over 2. We want to be able to use the value that is within that domain in the range. So this is going to be negative pi over 2. Okay. All right. Take a moment and try 16 through 24. All right, class. So after attempting 16 to 24, let's just double check to make sure that you got it all down. So for number 16, you should have seen pi over 4. For number 18, right, calculating that negative 3 pi over 2, sorry, negative root 3 over 2, from that 5 pi over 6, we do get a 5 pi over 3, but kind of keeping in mind, how do I rewrite this within that domain? So it should be negative pi over 3. So kind of taking a look at our unit circle, we're coming over here to 5 pi over 3, and that's going to be equivalent to that, oops, to that negative pi over 3. So again, just keeping in mind the domains and the ranges for these functions. So number 20, we should have gotten a similar thing, right? So it lands as pi over 4, but it really should be negative pi over 4. And then for 21, we get root 3 over 2. I skipped number 19, sorry, I should have gotten 0. For sine of pi over 4, we should get root 2 over 2. For sine of arc cosine, we should get 1. And then for tangent inverse of root 3, we should get cosine of pi over 3, so therefore we get 1. So now we're going from the arc tangents and the tangent inverses to the original trig functions. All right, let's take a look at the non-unit circle values. So when you're looking at these, we're going to first, let's start by looking at the inside, and we're going to assume that that's equal to some theta. So looking at our particular number 25 here, we have cosine inverse of 8 over 17. Let's think of some things about cosine. So we know that cosine theta is positive, so it's greater than 0 in quadrant 1 and quadrant 4. And we know that cosine inverse of theta is defined within quadrant 1 and quadrant 2. So because of this, this tells us that we are looking specifically at quadrant 1. So therefore, anytime you see 3 little dots like this, it means therefore. Therefore, our theta is going to lie in, so it's going to be an element of quadrant 1. Okay. All right. So let's take a look at this now. So we're going to let theta equal cosine inverse of 8 over 17. So this implies then that cosine theta is equal to 8 over 17. So we already established that we are in quadrant 1. So let's take a look at our triangle. So here's our triangle. Here's our right angle. Cosine is going to be our opposite. So we have 8 over I hypotenuse 17. So let's go ahead and calculate. We're going to use the Pythagorean theorem here. So we end up with 8 squared plus, let's call this, oh, you know what? I set this up wrong. Sorry, class. This is my adjacent. Let's call this x. X squared equals 17 squared. So then we get 8 squared is equal to 64 plus x squared, which is equal to 17 squared. We're going to subtract the 64 from the 17 squared. So when we subtract that, we end up with x squared equals 225. And so we take the square root of that, we get that x is equal to 15. So this equals 15. And so now we're taking the tangent of that theta. So tangent of theta is equal to, remember, that's going to be opposite over adjacent. So my opposite over adjacent is going to be 15 over 8. And that's my value. All right, take a moment and see if you can figure out number 26. Looking at number 26, we have sine of arctangent of negative 12 over 5. So let's start off here looking at the arctangent. So we know that tangent theta is less than 0 or is negative in quadrants 2 and quadrants 4. And we know that arctangent or tangent inverse is only defined in quadrant 1 and quadrant 4. So the overlap is happening here in quadrant 4. So this tells us that our theta is going to be located in this quadrant 4 here. So we're going to start off by letting theta equal that tan inverse of 12 over 15, that negative 12 over 15. So that's telling us that we are going to have tangent of theta is going to equal negative 12 over 15. Drawing out our triangle here, right, we have, because tangent is opposite over adjacent, we get the 12 and the 5. So we're really trying to find that hypotenuse. Using Pythagorean theorem, we find that our hypotenuse is equal to 13. And so that tells me that the sine of theta is going to be the opposite over the hypotenuse, which is that 12 over 13. We know that the product is negative because, remember, we are in that quadrant 4, so our sine should be negative. So this would be our final answer. All right, hopefully all of this is coming together. Again, we will continue to practice this in class.